Okay, so I want to continue with the hashing today. So did you try it like throwing documents into a shelf? Did you try hashing your documents to a table? So let's try and do that today, how we can do that so that we get good properties. So what good properties? Basically, you have formally a set of keys and a subset you want to store somewhere. And what you want is you want to do search, that is lookups, whether some key is in the table. You may want to do insert delete, of course. And there are, we said, two types of structure. One is a static, where the set, once fixed, doesn't change much. Another is dynamic, where you may do a lot of insertion deletions. So static example is, say, a dictionary or book index or whatever. And a dynamic would be like you maybe routing table or a table for, say, some warehouse where you are actually like, there's a lot of items going in and out from the system. Okay, and we said we are going to do hashing. So because of this order 1 requirement, so if for the static, generally one first thing that comes to mind is like sort the keys, right? And then you can do lookups, because in the static case, most of the time you are going to be doing a search, and then if you sort it, then you can do like login time searches. And for the dynamic, it's balanced binary tree, right? Again, insertion, deletion, search would be login. So, but we want order 1, so we said let's try something very, very different. We don't want to store data in any sorted order. We will use something called hash functions. So here you have a table T of say size m. Then there is some function h which maps every key in the universe to a number 0 to m minus 1. So when you want to store x, element x, then you compute this h of x, which will create one of these numbers, 0 to m minus 1, and then store x at t of that number, t of h of x. So for any given set S, for any element in the set, you compute h of x and store x at that slot in T, okay? So if you want to do lookup, you compute h of, so you want to check whether y is in the table or not, then you compute h of y and look at this location in the table, and if it is equal to y, then you are fine, it's there, otherwise it's not. And the hope, the kind of ideal hope would be no two keys map to the same location, otherwise how would you store it, right? But this is impossible. If the size of table is less than the size of universe by pigeonhole principle, some two keys has to map to the same position, right? And so we said in that case we are going to store a linked list at every position, right, in the table. So the entry in the table points to the starting point of the linked list, and whatever elements map to that position, that location, that slot, all of them are stored in that linked list. So when you want to look up, you go first to that location, look at the starting point of the linked list, and then search the linked list. And for searching linked list, you just have to go like step by step, maybe all the elements you have to look in the linked list to find out whether some key is there or not. So the running time would be it will depend on what is the size of these linked lists, okay, at every position. So the question then is, does the hashing actually give order 1 time? You could, if the linked lists are very, very long at any position, then it's not good, right? If you hash all the elements to same position, it's no use. Basically, you are just storing a linked list, right? And it may happen. So if you suppose my n, that is the size of the universe, is at least m square, okay? Then any hash function I take, any hash function, from this u to 0 to m minus 1, u to t, there exists some position in the table which will have m elements, again by pigeonhole, right? Because there are m positions, m square numbers. If you are giving m different numbers to any of these m square keys, all of these m square keys, there will be at least m keys who will get the same number. If my set contains all of these m keys which maps to the same position, then this hash function is really, really bad, right? Because to search any key, I'll take order m time. Okay. So this is no good. So we have to do something clever, right? So the first lesson is we have to consider a set of hash functions with some good properties, so that for the other thing is we should not be picking h deterministically, right? Because for any particular h, there will be a bad set. And if your adversary gets to know your h, then it will try to like hack your system and choke up your hash table. Okay, so we want to use randomization, and then the guarantees will be in expectation. So we want small number of collisions in expectation. And the other thing should be, because we are going to be kind of picking a hash function from this family, like we will be like sampling it, so there should be efficient sampling allowed from our hash family. Okay, so this point is clear that we have to use randomization because of this problem, right? If you fix a function, there will be always a bad set. So just to remain one step ahead, we will not pick it deterministically, we'll pick it randomly from some family, which allows efficient sampling. Okay. So what are these good properties that we are talking about? So good properties in intuition are that there are number of collisions in expectation should be small. Okay, when we pick a function at random from this family. So let's formalize that. Okay, so consider any element x from the universe. Now let's pick a hash function from this family at random, uniformly at random. So every function has the same probability of getting picked. Then the probability that x will get mapped to position I when h is picked at random, that is 1 over m for any x and for any I. This guarantee is clear? So I have, say, a set of hash functions. I fix x, I fix I, element in the universe and a position in the hash table. Okay? Now I pick a function at random from this family. The probability that h of x will be I is 1 over m. Okay, this is called uniform. Now I am going to give you, so suppose my family is this. It's a constant function. So every element in the universe maps to the same position. How many functions are there in this family? So there is a function h0 which maps every element in the universe to 0th position. h1 maps every element in the universe to 1st position. h2 and so on. Okay? hj will map every element in the universe to jth position. How many functions are there? So there are, because there are m positions, 0 through m minus 1. So there are m functions, right? What is the probability? What is this probability for this family? So fix x, fix I. Now I pick a function at random from the family. What is the probability that h of x will be I? 1 over m. So this seems like a good property, but it doesn't capture what we want, right? Because we are mapping all the elements to the same position. So there are a huge number of collisions. right? So we want something stronger. So these are called uniform functions, but that can be uniform family, but there can be really bad uniform family. Second is universal, which actually says that if you take any x and y, distinct, and then if you pick a function at random, then probability that they will collide, so h of x will be h of y, is 1 over m. Okay? And this is good. We'll see why. This is what we want. So let's define such a family where for any two distinct xy, when we pick h at random from the family, then h of x equal h of y is 1 over m, this probability. Then we call it universal. It's also sometimes called 2 universal because we are saying that no two elements collide with more than 1 over m probability. You can extend this to k universal where you can have like k elements don't collide with 1 over m to the k probability. K minus 1. Okay. So why we are looking for this? Let's say if we have such a hash family, then why we will be doing lookups very fast, like order 1. Okay. So we are fixing the set S. Now we are asking what is the expected time to look up some element x in this set S when h is picked uniformly at random from the family. This is the main question, right? Expected number of lookups to check whether some element x is in the table or not. So let's say L of x is the size of the list at the position t of h of x. So h of x is the position, location of element x once we fix h. And look at how many elements get mapped to the same position. Okay, that is L of x. Once we fix h after this, right? So L of x is a random variable in that sense, right? So we want to compute the expectation of this random variable. This point is clear why L of x is a random variable? Because this position h of x is fixed only after you fix h, right? And then you are asking once you fix h, how many elements map to the same position as x's position? Okay, as you change h, this number is going to change. So this is a random variable. And let's say for y, for any other element y, we define dy to be the indicator random variable, which is 1 when h of y equals h of x. So y and x map to the same position. Then clearly the L of x is just summation of dy, right? You're counting 1 for every element that maps to the same position, right? What is the, okay, so what is the probability of this happening when I'm picking h at random according to universal family? We just said it's 1 over m, right? So what is the expectation of this random variable dy? No, not Lx, I'm saying dy. dy is also a random variable which is 1 when y maps to the same position as x is x. The expectation is 1 over m, right? That is because that's exactly the probability that h of x equals h of y, right? So expectation of L of x is just by linearity of expectation, summation of expectation of dy, which is this, the probability of h of x equals h of y, but that is 1 over m, we just said, right? So this quantity is just size of s divided by m. And if the number of elements in the set are less than m, less than or equals m, then this is at most 1. So this is what this is. Does this remind you of something we saw last time? Balls and bins, right? What is the expected size of a bin when we are throwing n balls into n bins. We are exactly saying that. Throw m balls into m bins, because table size is the slots in the table are bins, and the elements of S are balls, right? So the expected bin size or expected linked list size at any position is order 1, or 1 actually, when S and M are exactly, S and T are exactly M size, right? So in general, if n is the number of elements in the set, then this expected size of the linked list at any position is order n over m. But, so expected lookup time is order 1, that's fine. So here also note that we have assumed that the set S is fixed. We are not changing, we are not doing insertion deletion. And let's fix that for now. We will talk about dynamic set later. Okay, our set is fixed for now. And we are just doing lookups. Okay? And for dynamic also, you will get good guarantees. We'll see how, if the number of insertion and deletion are order m. But remember, even in the balls and bins case, we saw that in the worst expected time, that is expected maximum bin size, is log n over log log n. And it will be the same analysis follows here. Okay, so if you pick a bin, its expected size is order 1. But when you look at all the bins together, take the max linked list size and then do the expectation. That can be log n over log log n. You see the difference between these two? Not clear? Good. Okay. And we will see how to handle this. So this is just a side comment for now, okay? Because I want to focus on those universal hash families. How do we create them, okay? And we will talk about how to handle this at the end. Okay, so let's get back to this universal hash families. So far we have just talked about it in abstraction. There exist, or maybe if we get such a universal hash family, then we are happy. But what are those universal hash families? So suppose I take all possible functions, hash functions. So all possible functions from the key set U to position 0 to m minus 1 of the set, of the table. We can show that it is universal. Okay, but what is an issue with this all sets, all hash functions? So what is the number of hash functions in this family? M to the size of U, right? Because for every key, it may go to any position in 0 to m minus 1, so the m possible values, so m to the size of U. Then what is the description, if you want to represent all of these, what will be the bit length of any hash function that you want to describe? It's a log of this, right? Which is huge, which is size of U times log m. This quantity is very, very huge, right? And this is not order 1, so this is no good. So we have to find compactly representable universal families. So let me propose one. Okay, so let's say n is the number of elements in U, m is the number of positions in the table, and n is the number of elements in S. Then pick a prime which is at least the number of keys, n. And look at the field ZP. Okay, what do we mean by field? So there is multiplication, addition, division, subtraction are well defined among these numbers. So you will be only talking about these finite number of things, 0 to mp minus 1, and you can define properly multiplication, division, subtraction, addition. We will see what do we mean by that. Now take any two elements from ZP such that A is non-zero, and then define this hash function which is ax plus b mod p mod m. So first you are taking the number, doing a linear translation, right? Then you do mod p and then mod m. Of course, you have to finally do mod m because your positions are 0 to m minus 1. Okay? And now look at all such functions for all possible values of a and b, where a is non-zero. Why am I enforcing a non-zero? If a is 0, then what kind of hash function do I get? Constant, which no use. Right? So note that the number of hash functions are p times p minus 1, because for b I have all possible values of 0 through p minus 1, and for a I have only 1 through p minus 1, so p times p minus 1. This is the number of hash functions I have. Right? Okay, I want to claim that h is universal. That is, I fix x, any two elements x and y from the from my U key set, and pick a function h a b at random from this family. Then h of x equals h of b. That h of x equals h of y. That probability is 1 over m, at most 1 over m. Okay, we will see why. So first of all, this hash family is of small size, so it is easy to sample, right? And second, every hash function, to represent every hash function, I just have to store a and b, which is small. Okay. So first of all, I want to kind of prove that ZP is a field. That means every element has a unique inverse in the field. Okay? So what do I mean by that? If you take an integer from 0 through 1 through p minus 1, 0 doesn't have an inverse. Every element from 1 through p minus 1 has an inverse. So that means for any x, which is from 1 through any number from 1 through p minus 1, there exists y such that xy is 1 mod p. Okay, this is what we mean by inverse of x. So if this happens, then y is an inverse of x. Okay. So let's see why. So first of all, I want to claim that if you fix x, y, z such that y not equals z, then xy mod p cannot be equals xz mod p. Okay, why is a simple algebra. Suppose to the contrary, they are equal mod p. Then it has to be the case that x times y minus z is 0 mod p, right? You're just subtracting xy minus, you're just doing xy minus xz. That means p divides either x or y minus z. But p is a prime, right? So p divides this product. But because p is a prime, it has to divide either x or y minus z. Do you see that point? Right? You cannot have two factors, one from x, one from y minus z, and that forms like p, because p is a prime, right? But p cannot divide x because x is less than p. So it has to divide y minus z. But y minus z is also less than p, right? So y equals z is the only possible. Now, using this, first thing we can say that there cannot be two, say y and z, such that xy equals 1 mod p, and so it is the same as saying xy mod p is 1 and xz mod p is 1. Right? Because we just said when y not equals z, if this happens, then y has to be equal z. This is what we've just proved. But why should there exist a y such that xy equals 1 mod p? So I'm giving you x. I'm asking about existence of y. Why should, I'm giving you a number x between 1 through p minus 1. Why should there be some other number y from 1 through p minus 1 such that xy mod p is 1? We again have to use the previous claim that if you take any two y and z which are not same, then xy mod p cannot be equals xz mod p. So okay, fix x. Now take all possible y. 1, 2, 3, 4, 5, 6, 7, up to p minus 1. You generate some numbers, right? So you look at xy mod p every time. How many numbers will you generate? P minus 1, right? Because no 2, you cannot have, say, x times 1 mod p equals x times, say, 100 mod p, because that's not allowed from the previous claim. So every time you generate a different number, right? And there are 1 through p minus 1 possible numbers. So there has to be some y which is xy equals 1 mod p. Again by pigeonhole. There are p minus 1 possible numbers. If you generate all of them, you are generating all of them, because you exactly generate p minus 1 distinct numbers. Okay, so now let me kind of tell you, so this kind of proves that ZP is actually field, and we can do this division. There exists, the inverse is like well defined here, okay? So let's do this, and we will use this property that if you take y not equals z, then xy mod p is not xz mod p, I mean very crucially in the proof. So the outline, how we are going to show that this family H, where every hash function is of type ax plus b mod p mod m, is actually universal. So we have to prove that if we sample a function from this family, then for any distinct x and y, they mapping to the same value, the probability is at most 1 over m. Okay, so this is what we want to prove. And just note that the number of hash functions we have is p times p minus 1. So we are going to prove it like this. Let's say that this function HAB is bad for this pair xy because we are fixing it, okay? So this is important, we are fixing x and y. This function is bad if they collide, okay? There are p times p minus 1 hash functions. If I can bound the number of bad hash functions, I'm done, because I'm picking a function uniformly at random from the family. So if I can prove that the number of hash functions which are bad is at most p times p minus 1 over m, then I'm done. So this is simple counting, the basic method, simplest method to kind of argue about randomized algorithms. Counting. So basically we have to kind of count the total number of hash functions such that where these values collide, like in a brute force way in some sense. Okay, so this is clear that if I count the number of hash functions under which x and y map to the same value, then I'm done. If that is at most like m fraction, 1 over m fraction of the total number of hash functions, and I'm done. Okay, so how are we going to do this? So let's define, so there are two mods we are doing in the function. Let's separate them first, okay? Because mod p has good properties. When every number x and y you take are less than p minus 1, less than or equals p minus 1, okay? So let's define G function, which is Ax plus B mod P. And then H is just do G and then do mod N. Okay? So now first of all, if we take some two keys X and Y which are not equal, let's say R is when G applied to X and S is G applied to Y. First thing you can kind of intuitively see that, so we didn't exactly prove this, we just, when we had B equals 0, we already proved that R cannot be equals S. Right? But this adding plus B won't make much of a difference because it will cancel from both sides. Okay? So first thing we will prove that R cannot be equals S. If X not equal Y, then R cannot be equals S. Okay? So first mod doesn't collide them. So that says that if you take any xy, we fix it and you vary A and B. So xy maps to, for fixed AB, suppose it maps to RS. As you vary A and B, it will vary S, R and S. And there are P times P minus 1 possible values of A and B. And that will generate exactly P times P minus 1 possible values of R and S. Okay? So when we say R not equals S, suppose this is a P by P matrix, so there are P square elements. Right? If R cannot be equals S, that means you are excluding the diagonal. Right? So suppose you are plotting R here and S here. Right? So then how many possible RS pairs are there? P times P minus 1, right? And I'm claiming that as you vary A and B, because you are sampling this function HAB, you create all possible values of R and S. This pair R comma S. Okay? So there is a one-to-one mapping between AB and RS. Then you do mod M. So basically you are kind of collapsing this P by P matrix to M by M matrix. Okay? So even though plus first mod didn't collide them, so you are kind of excluding the diagonal when X and Y are not same. Second mod, when you do mod M, they may collide. So there might be some pairs R and S. When you do R mod M and S mod M, you will get something same. You could have R mod M equals S mod M. And you want to exactly count that how many cells in this square actually collide to any of the diagonal entry in the smaller matrix. Right? Because diagonal entries are exactly saying that R mod M equals S mod M. Okay? So you may have some squares here which may collide, which may go to a diagonal when you collapse it through M by N to M by N matrix by doing mod M. And we want to kind of argue that this is at most the 1 over M fraction of all the possible squares. Okay? So what did we say? We said that let's do first mod M and then mod P and then mod M, and then look at this as a two-step process. So when X not equals Y and you apply this G function, so you do mod P, then you go to some non-diagonal square. In fact, every time you change AB, you will go to a different square, not on diagonal. Because there are P times P minus 1 possible values of AB, you will generate P times P minus 1 possible values of R comma S. And these are exactly the number of possible values of RS. Right? If R is any number between 0 through P minus 1, and S is any number between 0 through P minus 1, and R is not equals S, how many numbers are there? How many pairs are there for RS? P times P minus 1, right? So there is one-to-one correspondence between RS and AB. And then when we do R mod M and S mod M, at most 1 over m fraction of RS pairs will map to the diagonal in the small matrix. That means at most 1 over m fraction will have R mod M equals S mod M. Okay? So let's try and do this. So basically we need these two lemmas. First, one-to-one correspondence between AB and RS, all possible. So these are the all possible values of AB and RS. These are P times P minus 1, and we want to define a one-to-one correspondence between them. And then argue that at most 1 over m fraction of RS can have R mod M equals S mod M. Okay, questions? Okay, so let's try and do the math. So first thing, R not equals S. That means if I take X and Y, two keys, which are not same, and do AX plus B mod M, mod P, and AY plus B mod P, they cannot be same. Again the same proof, right? Suppose to the contrary they are same. Then B will cancel, and you will again get A times X minus Y mod P is 0. Again, because P is prime, it has to be the case that either A mod P is 0 or X minus Y mod P is 0. But A mod P cannot be 0 because A is less than P. Right? So it has to be the case that X minus Y mod P should be 0. And this is also not possible if X minus Y is not 0. Right? Because X minus Y cannot divide P, since P is a prime. And A is less than P, and X minus Y is also less than P. Okay, so this is simple. Now the second question, one-to-one correspondence between AB and RS. So the lemma says, if X not equals Y, then for each RS, such that R is not equals S, because we already said that if X not equals Y, then R cannot be equals S, right? So we just look at those pairs. Such that R and S are between 0 and P minus 1, there exists one AB such that AX plus B mod P equals R and AY plus B mod P equals S. So you are kind of solving a system of equation mod P actually. So I'm giving you XY and RS, both. And I'm asking what AB will generate this RS when applied to XY. Okay, it's a reverse question. And it kind of boils down to exactly solving system of linear equation. So think of A and B as variables, and R and X as, and Y and S as constants. Then you have two linear equations. If there was no mod P, then you can like uniquely define it, right? Because you can say that subtract AX plus B equals R from AY plus B equals S. That gives me A times X minus Y equals R minus S. And then just divide, because X not equals Y, so X minus Y is not 0, right? So A is just R minus S divided by X minus Y. And once you have A, you can find B. Just plug in the value of A here. That's exactly we did, right? AX, so B is R minus AX. Questions? This is the most annoying thing about Microsoft. Can I have another RS which gives me same values of A and B? So given RS, so X, Y anyway are fixed, so forget about that. Given RS, I am generating A and B with these formulas. Right? Now suppose I give you another R prime, S prime. Can they generate same AB? Why? Exactly. The question is clear? Okay. So I'm saying I hope I want a blank page. Blank page. Yeah, so I'm saying that, so I kind of said that I have fixed X not equals Y, and from RS I generated AB with some formula, right? With this formula. Can I have some R prime, S prime, which generates the same AB with the same formula? With the same formula. So I say there exists another R prime, S prime, such that this happens. So basically I'm saying that I get this. No. Why? If no, then we are getting a one-to-one correspondence. I'm sorry, what's her name? Say? Sheeling. Okay. She gave some answer. Sheeling gave some answer. So note that you get these formulas from these formulas, these two, right? So if for R prime, S prime, you get this equality, you can kind of revert it back to get this. But we already know, because of this current lemma, that this is equals R and equals S. So it has to be the case that R prime equals R and S prime equals S, right? Because it's simple. I mean, it's a trick question. Yeah.
So when we solve two equations, why did mod P move from left side to right hand side? Like, it was AX plus B mod P, and then in your proof it's R mod P.
It's just way of writing, actually. Finally, you are doing. So finally, what I want is this, right?
Right.
So it's just when you say some two numbers are same as same mod P, under mod P. So say I'm doing mod 3. Okay, I can say that 4 equals 1 mod P. Okay, it's same as saying that 4 mod P is 1. It's just way of writing it. Okay. And why we did this right like this? So that, because finally I want to find A and B, which I know are at most P minus 1. So just when I write it, it's convenient to see. That's it. Okay. Okay, so this gives us one-to-one correspondence between AB and RF. This is a crucial part. Okay, ask if there are any questions. Okay, so once we have this, we are kind of going to do second step, which is modern. So let's say we kind of think of this, as we said, as two steps. First we compute step, which does AX plus B mod P, and then fold step, because we are going to collapse. So in the first step, we didn't collide any distinct keys. All distinct keys went to distinct positions, mod P, right? Distinct values under mod P. But when you do mod N, they may collide. So let's call it fold. So now the question is, given 2 X and Y, they may collide. So what is the number of not equal pairs of R and S such that when we do the fold, they become the same number? There is a collision. How many such R and S are there? Okay, that is the main question now. Right? So take a pair, okay, R not equals S, from this set. Now fix R, okay. Then we'll get something for the value of R mod M. Okay. Let's say that is A. I want to ask what different values of S will give me exact, when I do S mod M, it will give me A. So there are how many possible values of S? P, right? And we know that M is less than P, right? So suppose A is 1. Okay, and say P is, let's say M is 3, and let's say P is prime, 17. Okay, so M is 3, right? A is 1, or let's say 0, simple, even simple. Okay, A is 0. And P is 17. So S can take any value between 0 and 16, right? What values of S will give me, when I do S mod M, I get 0. M is 3. 3, 6, so first of all 0, right? Then 3, 6, 9. So how many are there? P over M, right? Out of that, 1 is exactly when R equals S. So discard that, because we have assumed that R not equals S, right? So there are P over M minus 1 elements for possible elements for S when we get R mod M equals S mod M. And all the possible values for A are P. So it's like exactly this value. Multiply this by P. Because we have to talk about all possible values of A. Right? So we have to talk about all possible values of R. Right? So we get that this is at most P minus 1 times P over M. This is exactly we want. So if we put everything together, we get the proof. So first we said that just apply mod P, we get R and S, and we know that R not equals S. So in the first mod P, you don't get a collision. Then you do mod M, and then things may collide. But we showed that out of all possible values of R and S, which are P times P minus 1, at most P times P minus 1 over M will collide. And there is one-to-one correspondence between A, B and RS. So as you change the value of Rs, the value of AB is going to be changing. So you cannot generate two values of R comma S with the same AB. So if there are P times P minus 1 over M bad values of Rs, which actually collide, then there has to be exactly those many AB which makes X and Y collide under the hash function. That's why this one-to-one correspondence was important between Rs and AB. And because we are picking a family, one hash function at random from P times P minus 1 possible hash functions, and at most P times P minus 1 over M are bad, so the probability is number of bad AB pairs, number of bad hash functions divided by total number of hash functions, which is the P times P minus 1 over M divided by P times P minus 1, which is 1 over M. Yeah.
Why is the 4 point important?
Because I am not choosing Rs. When I pick a function at random from the family, what am I choosing? So I have to be talking about how many of these hash functions actually forces h of x equals h of y. I have to count that, right? But instead I counted Rs. So I have to kind of connect it back to the hash functions themselves. Okay, this is a very important point. So, I mean, in the entire proof, I just counted bad Rs, right? Bad meaning R mod M equals S mod M. How many bad such pairs are there? But that's not picking the function, right? Rs is generated by the function. But we already established one-to-one correspondence between Rs and AB. As you pick different function, you are going to get different pairs of RNS for RNS, right? So this is basic counting. You have P times P minus 1 total number of functions. How many functions actually forces h of s equals h of y? You just counted that to be at most P times P minus 1 over M, and that's why you get 1 over M. Sorry?
Is there a way to filter out this kind of variation?
Good. So what do you mean by that, filtering out?
I mean, you maybe through deduction, you realize if AB has some, if for certain AB they follow some specific function, they will be bad. Then after you generate it, you can have if they are.
Okay, so here this is another important point. Okay, probably I didn't stress it enough. All of this analysis was after fixing two elements x and y. So you have, what I did was counted, fixing x and y not equal, they are not equal, x not equals y. I counted how many functions are bad for this x and y. Now I change x and y. So keep the bad set. Let's say bad x and y, x comma y. This is a bad functions which makes x and y to collide. Now suppose I change x and y, x prime, y prime. Will I get the same set of function? Or different? Okay, there are like, if capital M is the number of keys, there are like n choose 2 different possible values of x and y. Right? We just counted number of bad function for a particular pair of x and y. Now I change that pair I take another two different keys and ask what are the bad functions for this two keys, which makes them collide. Will that set same? Will that set be the same? This question has to be answered to understand why we are using randomness and why we are doing all of these. If that set was same for all x and y, for all x not equals y, then you are right, we should just exactly do that. Remove those hash functions. Now keys will never collide. Right? But unfortunately, they are not same. Right? As you vary these pairs, you actually will go over all possible functions in the hash in your family. So every function is a bad function for some keys. Okay? Now the point is, your set is not all the keys, it's a subset. Right? And typically the universe is much, much bigger than the subset that you want to store. Right? And that's why when you pick the function at random, so remember the possible values of a and b are p, and p is at least n, the size of the universe. Right? So you have at least n squared choices of picking a hash function. Right? So now when you pick a function at random, you hope kind of that for your set this function is good. Okay? Now if you have a static set, again you can ask this same question again, right? If your set is fixed, you can do a priori computation and see for every pair in your set what functions are bad and remove them, right? But sets are generally not as static, right? Static meaning you are not making too many changes, maybe one or two in a day or something like that. Right? And that wouldn't work for dynamic sets at all. But that's a good point. Okay? It has to be understood that why we are not just discarding bad functions from the family. Because it's not possible. Because every pair of xy will generate different set of bad functions. Okay. So what is the lookup time? We had proved that if the family is universal, the expected lookup time is 1. But we had already noted that, like in balls and bins, in worst expected lookup time could be log n over log n. Okay? But all of these are under the assumption that the size of the table is almost same as the size of the set. What if, is it visible? Oh, it's not visible at all, sorry. What if the size of the table is the square of the size of the set? So now you are throwing m balls into m square bins. Okay, then I claim that the expected max size of any bin or any linked list is now order 1, not log n over log n. Okay, so one thing you can do is, instead of picking a table of size m, pick a table of size m square. But that is quadratic increase in the space. Suppose I don't want that, I want still linear size space. So if I want to store m elements, if my size of set is n, then I still want to keep the table size order m. Then what do I do? Or not table size, but like total size that I use total space I use to be order m. Okay? And I also want this property, that expected max lookup time is still order, I want order 1. Okay, so this is a very nice trick. What you do is, your set is fixed, remember? So you do hashing once. Now go to every position. You have a linked list there. If the linked list exceeds some number, say 10, you construct another hash function just for that linked list, but with the square of the size of the linked list now. Okay, so the procedure is clear. How do you do it? It's a 2-level of hashing. You do first hashing, then you go to every location, see how many elements are hashed to this location. See that list. If that list is long, too long, say more than 10 or 20 or whatever, you create another hash table only for that list. But now the size is the square of that linked list, size of that linked list for that second level of hash table. Okay? So for some you did create second level, for some you may not have created second level. This is called perfect hashing. Why? Because it has both good properties. First, worst case expected lookup time is order 1. Second, the space you use, total space of both levels, is still order m. Okay? So you see, this will just follow from the previous, from this. Why? Why is that? The first lemma follows from the fact that if you throw m balls into m square bins, then expected max bin size is order 1. What you have to do to look up an element in this new hash table? So what will you do? The first thing you will do. You have the first hash function, you compute the location. Go to that location I will be either pointing to the starting of the linked list or giving you another hash function. Right? You compute another hash on the same key and go to the second level of hash function. You know that in that no linked list size is more than order 1, right? So whichever position you go in the second hash table will have order 1 linked list size. Right? That's what the previous lemma is saying. Because this m is the size of the linked list which is going to the next hash table, second level of hash table. So the first lookup to go to the first location in the first linked list, second lookup to go to the second level of linked list, 2 lookups, and then in the second level of linked list you know that every linked list size is order 1, so only order 1 lookups in expectation. So, and you can try and prove this. So it's basically this yi will be a random variable. You have to kind of compute the expectation of sum of the yi squares. You can try and show that it's order 1, order m. Okay. So let's try and do the main claim. So now we are throwing m balls into m square bins. Okay, I want to just repeat kind of the analysis we do in the last class for m balls to m bins. Okay. So what is the probability that ith ball lands into jth bin? So we are throwing m balls into m square bins. 1 over m square, right? So now if I'm looking at the size of any particular bin, what is the expected size of that? 1 over m, right? Because I'm throwing m balls, any particular ball landing into this bin is, the probability is 1 over n square, so at most kind of expectation is 1 over m. M times 1 over n square is 1 over m. Now expectation is very, very low, right? Previously it was 1, now it's 1 over m. So now I can ask, what is the probability that yj is greater than some order 1, say 3 or something? Because expected value is 1 over m, which is very, very low compared to some constant, say 3. So I should get some very tiny probability for that. And that will kind of give us what we want, right? That the max size is 1. Right? So let's say C is some constant which is at least 3. And I define delta to be, say, Cm minus 1. Now I want to bound the probability that what yj is greater than C. Now I can write C as just Cm over m, but Cm is just delta plus 1. And 1 over m is just expectation of yj, right? Again, I can show that all of these events of throwing individual balls into bins are independent. And that's why I can apply Chernoff bound. And I kind of put a Piazza note that there was a wrong Chernoff bound we used in the last class, and this is the right formula we have to use. These are tighter than the Chernoff bound that we used last time, and this will help. So because this value delta can be greater than 1, so we have to apply this formula. And when you simplify this, you get that this is at most 1 over m cube. You can go over it on your own, but finally you will get this quantity is at most 1 over m cube. So any particular bin has more than 3 size, that probability is at most 1 over m cube. What is the probability that any of the bin has, there exists a bin which has more than 3 size? 1 over m square by union bound. Sorry, 1 over m, because there are m square bins. So it has to be 1 over m, right? Because 1 over m cube times m square for every bin. So that's 1 over m. So the probability that every bin has size at most C is 1 minus 1 over m, which is a good enough probability. I can boost this probability more, like n square m cube, by increasing this constant here. Okay? And then you can kind of calculate that even expectation, because of this, the expectation will turn out to be at most C plus 1, which is order 1. Okay? So you can get rid of that log n over log n in the worst case also by doing this 2 levels of hashing. And what if your set is not fixed and it's changing? You're doing too many insertions and deletion, say kind of around order m. Okay? Or suppose you couldn't guess your set size. You guessed that your set size will be s, but finally you ended up adding more than some constant time m. Okay? You couldn't guess your set size a priori properly. Then you can do rehashing. So you rebuild your hash table periodically. That is the solution. And still your amortized analysis, amortized running time will be order 1 for everything. Okay? So what you do is choose a new table size based on how many keys currently you have in the table. Choose a new random hash function and rehash, and discard the old hash table. So when should you do this? So if your size grows more than twice, say, or if you do, say, 10 times more than m number of insertions and deletions, okay, you can choose some constant. Then you kind of do this rehashing, okay? That's the idea, and you can show that because every time you do rebuilding of a hash table, that takes How much time? As much as number of elements in your current hash table, right? And you already did so many insertions, deletions before you did a rebuild. So you can charge the computation of new hash table to those individual insertions and deletions. Okay? And that's why, so there will be at least those many new insertion and deletion before you did a rehash. And this is called amortized analysis. You kind of charge, you do something, you charge the time, running time of that to some events that has happened previously. Okay, because you wanted order 1 per insertion deletion lookup, so you can charge this construction of new hash table to those insertion deletions that you did before you did a rehash. Okay, and that's why overall it's order 1 still. Okay, and there are a few more things, but that's it for now. Okay, questions?
Do you have to store every hash function you mentioned?
Do I have to store every hash function too?
You sample? Like you have to store every AB pair?
No, right? Because it's a sampling.
Then if you don't store it, like next time you want to look up a value.
So you just store the value that value of AB that for the hash function that you used, right? So that's what we mean by discard the previous hash table. So you chose a new table, you chose a new random function, you did the new hash. Now the old hash table is of no use. So you discard that hash function and that table altogether. So now you have only one hash function remaining.
So for one table, you only sample once.
Yeah. Yes, yes, yes. Okay. Thank you.